delighted to be here as part of this enterprise.
For everyone in the room, and we encourage you to tweet and do all that social media stuff using hashtag exploding dots, if you would, please. And so next up, I have the pleasure of doing a more formal introduction of James Tanton. He's the inspiration behind and one of our co-founders of Global Math Project, of course. James grew up in Australia. He came to the U.S. and got his PhD from Princeton in mathematics. He did a few stints of college teaching along the way, and then spent 10 years teaching high school mathematics. He's published several books. He's a mathematician at large for the Mathematical Association of America, and he spends his time traveling about and spreading the joy of math to anyone and everyone. His fellows started exploding out praise that we all know and love. Please welcome James.
Golly gee. Wow. Well, I am completely flattered and touched and honored, and thank you for Thank you for coming today. This is absolutely spectacular. I'm actually truly am deeply touched and honored. This is just amazing. So maybe I should say what the Global Math Project is, what the Global Math Week is, just so you know what we're doing. So let's see. It's actually Jill Denise's brilliant idea. She came to me about 3 years ago and said, "Hey James, you know this thing called Hour of Code, code.org. Have you heard of code.org?" Right, they brought coding to the world. They declared a special week in October, back in 2013, I think it was, just to say, students, please experience coding. Whatever level you're at, be C++, come to our website and do something spectacular with C++. Or if you want to just play with little bits of paper and learn what binary number arithmetic is, great. Wherever you're at, just have an experience with coding. And they've had a brilliant, brilliant success with it. I think they've reached over 250 million students at this point. And it's just beautiful and moving and stunning. So Jill said, we should do the same thing for math. And we said, yes, let's create a global math week where students can sign on to do some extracurricular math for an hour sometime during the week. Except we have a cultural challenge with math. Coding was deemed very exciting and appealing. A lot of people naturally sign up to do that, but most students, at least in this country, and it turns out most of the world, don't find math naturally appealing, exciting to voluntarily want to do that in your own time. But we have the wonderful, beautiful advantage. There are teachers all across the globe. Teachers are the best and most stunning and fabulous advocates of joyful mathematics. When they give them the freedom to do joyful mathematics with their students, they will and do, and they're the best advocates for it. So we started Global Math Week with the idea of reaching out to teachers and setting mathematics free for them to have that joyful, uplifting, human, meaningful experience with their fabulous students in their classrooms sometime during Global Math Week. That's all they had to do. And we chose the topic of exploding dots because my background is somewhat unusual. I was in the whole math research world. I got my PhD at Princeton, and I came here in 1988 for that. And I looked at the curriculum, and I decided to become a high school teacher. I was a high school teacher for 10 years in Boston. So I've been thinking deeply about the mathematics and the curriculum, and my mission is basically just, can we make this a meaningful, joyful story for one and all that actually attends to the mathematics and attends to the humanness of mathematics, the creative, organic experience of math. And I was teaching polynomial division to 11th graders in the school and thinking, first of all, why am I required to teach polynomial division to high school students? I do not recall dividing polynomials as a mathematician myself. I could probably nut my way through it if I had to, but that's the point. I could nut my way through it if I had to. And I realized it's not the polynomial division's important, it's just the vehicle for teaching the thinking. In fact, that's kind of what really propelled the story of exploding dots, which I'll go through with you this morning. It was actually polynomial division. And I will start today, my story of polynomial division, how I exactly start with every audience, be it kindergarten, grade school, middle school, high school, college, parents, professors, no matter what. We start the same way because what's really important here, people don't realize mathematics is actually a story. It's a human experience. Let's share that. And there's no such thing as, elementary math is elementary. Elementary math is actually the portal to the wonder and the joy of it all. So let's focus on that and see how it opens up and deepens to these huge abysses of that are scary and daunting and fabulous and wondrous at the same time. So we started Global Math Week, and we brought exploding dots to the world. And last year, October 10th, was the start of Global Math Week. In fact, we're going to choose 10-10 every single year. Do you know why we chose the date 10-10? Oh, didn't even think of that. Oh my gosh. Okay, well, I'm Australian. How do I read the date 1010 from Australia as an Australian point of view? It's 10th of October. In America, how do you read 1010? October 10th. You won't go wrong with 1010. Except we failed on one thing about being truly international. We are calling ourselves Global Math Week. What's wrong with that? Because I grew up with maths. I know. Okay, but we failed on what to do with that S. Anyhow, but everyone understands Global Math Week. All right, so we did this. We opened up the doors. We created this spectacular experience of exploding dots. We made videos and wrote book chapters, and this spectacular company in Montreal called Scholab produced the most amazing web app of the experience as well. But we're fully aware that classrooms across the globe have all levels of technology. Full laptops, experience in the laptop in the classroom, go for it. We got it for you. Minimal technology, can you project a video? Great, just project a video. Or if you've got nothing, for example, I got an email from someone in Zimbabwe who had nothing in his classroom, and he said his kids went out to the schoolyard, they actually dug holes in the ground and used stones to mimic exploding dots. If you've got no technology, it's accessible to you as well. So we did this. We brought this to the world last year, and we did not believe we were going to get anywhere with this. We had this audacious goal to reach 1 million students. I remember at 11:56 a.m. on that Tuesday morning, the first time, I was sitting at my laptop. I was obsessed about my laptop, watching the calendars go by. We reached 1 million students at that moment, the first day of the week. And by the end of the week, we'd reached 1.77 million students across the planet, about 150 different countries and territories, just doing exploding dots, having a common experience sometime during that week, and sharing it on social media. Unbelievable. We proved to the world that actually if you set mathematics free, you set teachers free to have the joy of mathematics, they will gladly open up their classroom doors and have mathematics speak and shine for itself with their students. Unbelievable. It has since grown to 4.8 million students to about 170 different countries and territories, which is amazing. So this year we're doing it again, popular demand, exploding dots, and our goal is to reach 10 million students, which is beyond audacious. Someone used the word audacious already, beyond audacious. But why not? Because this is the experience. So I'm going to go through the exploding dots story. But let me tell you that our ultimate mission is really make this accessible to the world. Our materials are available in French, Montreal, thank you, and Polish, thanks to the Fundacja Viva in Poland. They really took on exploding dots. And we've also been working to translate our materials into other languages. For example, we recently had everything translated to Spanish, which is spectacular, and Swahili. Because one thing we've discovered the power of individuals that are passionate about mathematics in local communities can do powerful things. And what we'd really like to do is work on this as we grow and develop, give power to the individuals. For example, Eric Matthew Kaya in Tanzania, Arusha, really has taken on exploding dots. And he's rallied together a whole community of local schools. And they are actually doing exploding dots together. He's made a whole community of people that said, we need to translate everything into Swahili. And they did, as a community. All the written materials and all the web materials too. Not only that, he shared with me videos of their teachers in their classroom. Now, I grew up in a very Anglophilic education system where I had to like do, memorize, do, repeat, don't ever ask a question. It's actually taken to the hilt in Tanzania. But he showed me a video of one teacher who she was with a class. This was a high school class, but she did a long addition problem on the board, and everyone did it, 7 plus 9, carry the 1, blah, blah, blah. And she said, which direction did we go? We went left to right, right to left. And then she turned to the class and said, why? Why can't we go right to left? And it was the first time, apparently, that class had ever been asked a why question, and the whole class giggled. And they realized they could go left to right, and they got the same answer. Then they realized that if they're carrying, they could figure out what to do. She did exploding dots for the students in the way that they were now owning the experience for themselves. They suddenly realized they could ask, why is math always going from right to left when everything else goes from left to right? Transformative. And these kids were now owning mathematics. So our goal is, can we promote and foster that for more passionate individuals across the globe, because there are so many out there, and what can we do to support that? So our vision is try to, can we now bring the infrastructure to find and identify these fabulous passionate teachers across the globe, help them, support them in a way to make this action happen, because it does happen locally, and that's the way to change the world, we believe, locally. We've opened the doors, we've proved it works, let's just make it happen. Let's make it happen. So that's our mission. All right, so I had to say deepest thanks to those folks who have helped us make this particular event happen. The Overdack Family Foundation helped support this, as did 2 Sigma, as did McGraw-Hill Education, as did Oppenheimer Foundation, and also we have spectacular support from Great Minds, who are actually providing us lunch today. The Mind Research Institute is doing spectacular things for us today, and they'll tell us more about it. So they've been great supporters of our work, in particular with us today, day to day. MoMath has been a spectacular support as well, and I know that Cindy Lawrence has a little treat for us all as well, and I'll give her a moment to speak about that sometime during the day. Nancy Blackman in particular has been a spectacular supporter, and I have to just show off one thing which I've just seen for the first time now in physical print. Their latest Julia Robertson Math Festival booklet is gorgeous. Even though I'm very familiar with the material, I have to say so myself, this is stunning. So make sure you pick up a copy of this out front. In fact, we have a Julia Robertson Math Festival going on this afternoon at 3:30, and you're all welcome to come. And of course, we've got the Kickoff party tonight at the Tech Museum. Please come to that as well. Everyone's invited. And it's all grand. I have to also thank some people who've actually helped support the translation work. Tom and Bonnie Layton, part of the Akamai Foundation, actually supported the work to translate everything into Spanish, and that's just been a big, big help. And I actually managed to get some fabulous support from the friends at Simon's Foundation to do the Swahili for us. So I was actually able to help these teachers, not only just, well, they're in impoverished conditions. The fact that we could help support them to do that translation work with a little bit of income was just actually transformative for them. And they've taken that income and actually turned it around in the classrooms. It's just beautiful, absolutely beautiful. So thank you to that work. Of course, there's about 200 languages on the planet. How many languages are there? A lot. So we've got a long way to go. So we'll work on that. We'll work on that. So I'm sure if we're going to thank people, I will thank people more during the day as I realize what my brain is not doing right now. But the real key thing is we should do what we really should be doing, which is maths. Is that right? Let's do the maths. Would you like to see exploding dots? Shall we just go through it, just whip through it? Shall we have a speed exploding dots experience? You're on. But before I begin, those who know me know what I'm about to do. There's one very important piece of business. In fact, it's the only thing I truly care about, actually, honestly. Is everyone in this room aware that there was an international mathematics salute? And I mean it, dinky-dyed. There is an actual international math salute, a salute to mathematics. Would you like to learn it, for those that don't know it? The answer is yes. The answer is always yes today. All right, here goes. Watch out, it's strange. Arms have to be free for this. All right, arms out front. Right hand over left hand. That's the hard part, right over left. Then you go palm to palm. And then it gets weird. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, just come on back. What? What? Should I do it again? Yes. I'll do it close to the camera too. I'll do it up here. From a backwards view. Between the two cameras somehow. Okay, here goes. Arms out front. Right hand over left hand. I'm not cheating, it really is my right hand over my left hand. Palm to palm. Wiggle, wiggle, wiggle. And when you're ready, just come on back. Oh. Would you like some help? Okay. So I've given you a problem. So actually, this is a really good maths lesson for kids. It's a very good problem-solving strategy at hand right now. I've given you a problem, yes. But I've given you a very special problem. You know what the answer you're trying to get to. You know what the answer is. So what's a good strategy? If you know the answer to a problem, what could you do? Reverse engineer. It's a very basic strategy, but actually it's extraordinarily powerful, and it's good to be cognizant of this strategy. So let's do it. Here's the answer. So let's reverse engineer this. So you say, okay, where did this come from? Must have come from that. And if you lift up your fingers, I bet that feels very different from what you first did. Is that right? Okay, so I've half helped. I've started at the end, and we got to a funny feeling middle position. So your challenge now is, can you start at the beginning and somehow get to that same funny feeling middle position? The answer could be, oh, and some people are getting it. That helps some people. Yes, no? All right, so here's the deal. While I'm being particularly boring for the next 55 minutes, you can secretly practice it under the tables. I won't see you, so I won't be offended, and amuse yourselves. Yep? All right, okay, let's do it. Exploding dots, time for it. So we're in a tricky room. I am a Luddite when it comes to doing maths. I like whiteboards. So I'll do my best to write big so everyone can see over here, but it's going to be a challenge. If you want to move seats to over this side, we can all do it or not. All right, okay, here goes. Exploding dots. It all begins with a story that's not true. When I was a child, I invented a machine. Not true. And all the machine is a row of boxes. Is that big enough? That goes far to the left as ever you desire. And being a somewhat strange child, I gave this machine a somewhat strange name. I called it a 2-1 machine, written in a funny backwards way because I'm a young child and you know different. And the idea of this machine is you put in dots. In fact, dots will always go into the rightmost box. So if I've got one dot, zoom, there it is in the rightmost box. Not very exciting because it just stays as one dot. However, I put in a second dot, zoom. Then something exciting happens. Because whenever there are two dots in a box, they explode, kaboom, and disappear, to be replaced by one dot, one place to the left. Hence the name 2-1 machine. Do you get it? Excellent. So now I'm going to say the code for 2 is no dots, no dots, no dots, no dots, no dots, 1 dot, 0 dots. 1, 0. Here comes the third dot. Always the rightmost box. Zoom. So what's the code for 3 in this 2-1 machine? 1, 1. I have a feeling putting in a fourth dot is going to be particularly exciting. Are you ready for it? Here it comes. Zoom. Kabow! Dot. Kaboom! Dot. So what's the code for 4? 1, 0, 0. Can you see what 5 is going to be? 1, 0, 1. Can you see in your mind's eye what 6 is going to be? 1, 1, 0? Let's check it. You said 5 was 1, 0, 1. Here's the 6 dot. Zoom. Kajubal. Dot. Yep, 1, 1, 0. Brilliant. 13. Huh. 1, 1, 0, 1. Someone might be on to me. Any other predictions? Okay, we'll stick with that for now. But my point is, hours of fun working out codes in this 2-1 machine. That's all I was doing is working out codes. But then I had a flash of insight because I realized instead of doing a 2-1 machine, I could do a 3-1 machine. Very exciting. So how does that one work? 3 dots explode to become 1. So let's do it. Put in 1 dot. Not very exciting. Zoom. Put in a second dot. Zoom. Not very exciting, still 2. But put in a third dot. Zoom. Kabow! Dot. So 3 is 0. Okay. 4. Zoom. 1, 1. 5. Zoom. 1, 2. 6. Can you see it in your mind's eye? 2, 0. Zoom. Kabow! Dot. 2, 0. Beautiful. 13. Okay, he's on it. I think you guys are on to me. All right, 1, 1, 1 is the prediction. All right, but again, my point is hours of fun just working out codes of these machines. And then I realized if a 3-1 machine, I could do a 4-1. Okay, bold. Okay, bold. 10-1. I was going to say 4, but let's do a 10-1 machine. Okay, if we're going to be bold and audacious, let's be bold and audacious. Let's put in 273 dots in a 10-1 machine. Yeah, so my question is, what's the secret code for 273? Apparently it's 273. All right, I am not as fast as this fellow in the third row. So I'm going to actually do it. I'm going to put in 273 dots in this machine. Here goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I've got plenty of time, we're fine. So tell me when I've got 273. Really? Yes? Yes, right, all right. So I want to think it through. Here's a yes-no question. Will there be some explosions? Yes. Initially, how many explosions will there be? 27. Any dots left behind? Okay, so 27 explosions. Kaboom, kapow, kazing, kazoop, 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 kazoop. And you said 3 left behind. So I'll draw that. 3 left behind. And 27 explosions make a dot here each, so that means how many dots here? Can I just write 27? I'm getting bored with drawing dots. Is that okay? Okay. Any more explosions? 2. All right. Any dots left behind? Okay. Kaboom! Kajingle! And 7 left behind. So what is the secret code for 273 in a 10-1 machine? 273, just as the young lad said. All right, so what are these machines really doing? I know you're on to me. What are these machines actually doing? We're doing different bases. Yep. So let me just be really clear in my story here, because I'm a young child, remember? So we set up the 2-1 machine. Let's go back here. Dots here are always worth 1. 1 dot, 1 dot, 1 dot. And then we said, these, 2 1s, kabow! make one of those. So this dot better be worth 2 1s, which is 2. And 2 of these, 2 2s, kaboom! Make one of those. So this dot must be worth 2 2s. 4. 2 of these, make one of those. 8. 2 of those, make one of them scissors. 16. 2 of them scissors, make one of those scissors. Do you want to keep going, or should we stop? We'll stop. Okay. Now, let's check. This young lad told me that 13 was 1101 in this 2-1 machine. He said it was 1 dot, 1 dot, no dots, 1 dot. Can you see, and I mean literally see, whether or not he's correct? Yes, he is so correct. 1 8, 1 4, no 2s, and 1 1 does indeed 13 make. Wow. Welcome to base 2. The 3-1 machine. Dots here worth 1, but now 3 of these makes one of those. These must be worth 3. 3 of those make one of thems. 9. 3 of those make one of those scissors. Do you want to keep going, or should we stop? Okay. This young fellow at the front, near the front also said that 13 was 1 dot, 1 dot, 1 dot. Yes or no? One of those answers might or might not be correct. And yes, it's a yes. Because 1 9, 1 3, and 1 1 does indeed make 13. And a 10-1 machine, dots here worth 1. 10 of these makes one of those. 10 of those make one of thems. 10 of thems makes one of those scissors, and off we go. And yes, 273 is 273. I literally said the code. Why, literally, when we speak in English, we say 200s. Yes, we say 200. We say 7t. In English, that ty, what's that short for? 10. We're actually literally saying 7 10s and 3. We speak 10-1 machine. We call it place value in base 10, but there we are. In fact, we humans are just obsessed with the number 10 on matters of counting and arithmetic. Why?
10 fingers.
10 fingers. We so see these every day in our lives, we think, oh, this is the way to go. In fact, what do we call these individual things? What do you call the individual numbers? We are so obsessed with our hands, us humans. Though I happen to know that Martians only have 4 fingers per hand. So Martians would say, what's the natural way to go for arithmetic and counting? 8. They would say base 8. Brilliant. There are some cultures on this planet that went base 20. Where's that coming from? Apparently they're very aware of their fingers and toes. Yes. In fact, I'm in America. I'm Australian, but I'm living in America right now. The Gettysburg Address. Abe Lincoln. How did he start his famous address? 87 years ago. Okay, how many years ago was that actually? 87. Score is an old word for 20. He's actually speaking base 20 right there. 4 20s and 7 years ago. My French colleagues, how do you say 87 en français? 87. Which is literally, word for word, in English, 4 20s and 7. Speaking base 20. There are some cultures that went base 12. Very popular in parts of Southeast Asia and India. Because apparently they say there's a very natural way for us humans to count to 12 on one hand. Do you see it? It's unusual for us Westerners. They use their thumb as a pointer, and they notice that each long finger is divided into 3 natural sections, and they count to 12 this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that could be the reason why some cultures went base 12. In fact, we have lots of vegetables base 12 to this day, because 12 is a much handier number for us in matters of trade and measures and so forth. How many inches in a foot? 12. We always talk about dozens. How many things are in a dozen? So why are we obsessed with the number 12 in everyday practice? Because often in everyday practice, we often want halves of quantities, thirds and quarters. The basic fractions, half, third, and quarter. 12 is lovely. Half of 12, sure, 6. A third of 12, great, 4. Quarter of 12, 3, wonderful. 10, on the other hand, half fine, but then quarters and thirds come up a lot in daily life. 10 is actually really awkward. All right, so we can do lots of different bases. We can do base 8 for Martian, we can do base 20 for fingers and toes, base 12 for one-handed, anything you like. I will now stick with base 10 because we're in a society that's obsessed with our 10-ness, of our humanness, our physiology. So let me carry on, and I'll now work in a 10-1 machine. And I have to ask, okay, we're going to whip through the entire school curriculum now. After you know how to write numbers, what's the first thing you tend to do with numbers in math class? What's the next thing you learn? Addition? Okay, let's do some addition. All right, so clean the board. And we'll do long addition. I'm not sure which grade this is, but we'll do it. So, 543 plus 123. What's the answer? Yeah, 5 plus 1 is 6. 4 plus 2 is 6. Oh, 666. Didn't mean to do that. There we go. 666. Okay, but did you watch me? What did I do then? I went left to right. What would you naturally do? Right to left. Do you get the same answer if you go right to left? So what does it matter? Oh, I chose too nice a problem. Is that right? All right, so let's make it worse. Let's make it worse. In fact, this is a true part of today because I actually remember as a kid, I was being taught to read left to right in every class except math class. I was being taught I had to do everything from right to left in math class, which I thought was weird at the time. Anyhow, but the reason for it is something like this. 179. Is that better? Is that juicier? All right, 5 plus 1 is 6, 4 plus 7 is 11, 3 plus 9 is 12. 611 12. And it's correct. As a professional mathematician, I give my stamp of approval to that answer. It's absolutely fine. 611 12. I'm even saying it correctly. I can even draw you a picture to prove I'm right. Because the picture would go in a 10-1 machine, 5 hundreds, 4 tens, 3 ones. Please add 1 more 100. Sure, 1 more 100. Please add 7 more tens. No worries, here they are. Please add 9 more ones. Piece of cake. So how many hundreds do I have? 6. How many tens do I have? 11. Ones I have 12 of them. 611 12 is absolutely solid, fine mathematical answer. It's just that society thinks I'm weird. So how can we fix that answer up for society's sake? What can we do? Yes? We can let it kaboom! You want to do an explosion? Do you want to explode on this 11 or the 12? First. 12. You want to go right to left? All right, so we'll do 11. 10 explode. Kaboom! Leaving 1 behind, is that right? Yeah. Extra dot there. So it's now 701 12. Am I right? 1 12? Yes. Do another explosion. Kaboom! 10 explode. 2 left behind. Extra dot there. 722. Yes. I do not know how anyone learns English as a second language because most people say 20, though tutti actually makes more sense. It really does. And 1T makes more sense. By the way, I should tell you, Old English, look this up. They used to actually say 11T and 12T. They were valid. 12 tens was called 12T. 11 tens was called 11T. So I'm not quite as loopy as it first seems. So the standard algorithm that we were all taught back in our day, you go from right to left, you said. So you go 3 plus 9 is, you're not allowed to write 12, so what do? It really is 12, but you say 2, but one of these exploded, kaboom, and made an extra 10. So the standard algorithm, of course, is correct. It's just going right to left and does the explosions as you go along. Yeah. I prefer to go left to right and do the explosions at the end. It's just a style thing. That's all it is, just style. So do your own fabulous style thing. All right, so we've done it. Addition. What's next? What comes next? Yeah. Subtraction. Too hard. Let's do multiplication. So let's make something like, I don't know, 2784 times 3. What's the natural 3-second answer to that one? Yeah, okay. So you're doing it. So you're basically telling me, what, 6, 21, 24, 12, is that right? Because you said if I've got 2 thousands and 700s and 8 tens and 4 ones and say, please triple everything, well, 2 thousands will become 6 thousands. 700s will become 2100s. 8 tens will become 24 tens. 4 ones become 12 ones. So the answer is that. The fun part is saying it. How do you say it, if you can read my handwriting? 6,000, 2100, 2040, 12. Correct? Okay. 2040 sounds really weird. English is fickle to our ears. How does 2100 sound to you? Aren't we inconsistent? You will let me say 2100, but you won't let me say 21T. How you learn English, I do not know. So, could we fix this up for society's sake? What can we do? Kabooms, explode, yes. And I guess you've got two tens here, so at least 4 behind, extra 2 dots there. 6,000, 2,300, 2T, 40, 12. Off we go. We fix it all up. All right, great. So I'll go over here now. I did skip over subtraction. You're right. I shouldn't have skipped over subtraction. The reason I'm a little bit nervous about subtraction, to me, subtraction does not exist. There is no such thing as subtraction. To me, subtraction is the addition of the opposite, which puts me in a pickle right now, because I've been going on and on about these things called dots. So if I'm going to start talking about the opposite of a dot, well, I need two things. I need to know what to draw for the opposite of a dot and what to call the opposite of a dot. What would you like me to draw for the opposite of a dot? A lion? A line. Oh, my line's going to look like little ones. Okay, see, so a couple of people doing this to me, a couple of people doing this, some people doing this to me, and more people doing that to me. Okay, I'll do an open circle. More important question, what do you want to call it? Okay, so too many people know. It is so interesting to me. Todd is now becoming the very popular answer because of this. I'm actually a very boring person, and I've done this a lot all around the world. And up till recently, and I mean yes, up to yesterday, every audience I've been in that's been mostly all adults, they've always told me they want the word anti-dot. Okay? Anywhere in the world where the audience has been kids, the name that comes up, even if English is their second language, is Todd. Wow. And it's absolutely consistent. It's kids will say Todd, no matter where I've been in the world, it's always been Todd. I cannot even think of a time where it hasn't been Todd. But just be clear, where's Todd coming from? Dot backwards. Isn't it just gorgeous? Let kids be kids. Let our kids be kids. All right, but the idea is, it's like a dot and an anti-dot, like matter and antimatter. Put them together, and in science fiction, apparently they just go poof. They just annihilate. I won't say explode because I've already got explosions going, but I'll just say annihilate. I'll make a poof sound. So if I put a dot and an anti-dot together, I get this picture. That picture. Is that right? Okay, here goes. Let's do subtraction then. So if I did something like 547 take away 122, to me it's really this operation. It really is addition. 5 hundreds, 4 tens, and 7 ones. 547. Then please add 1 anti-hundred, Todd. 2 anti-tens, Todd. 2 anti-ones, Todd. Yep. Will there be any annihilations? Maybe. Poof, 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 poof. Am I correct? So 4 hundreds are left, 2 tens are left, and 5 ones are left. It's as though I went left to right. 5 take away 1 is 4, 4 take away 2 is 2, 7 take away 2 is 5, 425. Or was that too nice? Too nice. So let's make it worse. So I've already got the picture of 425 on the board. I'll start with that one. 425, take away 147. How's that? 4 take away 1 is 3, 2 take away 4 is negative 2, 5 take away 7 is negative 2. The answer is 300 negative 2t negative 2. Done. Done. Life's so much easier. I'm correct. I'll draw you the picture. 1 Todd, 4 Todds, 7 Todds. Wow, went for it. Poof. Poof poof. Poof 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 poof. Is it indeed 300s? 2 anti-tens, 2 anti-ones? 300, negative 2t, negative 1. Now the question is, that sounds weird in our society, so how could I fix it up for society's sake? Not math's sake, math is fine, but for society's sake, what could I do to fix that up? Okay, I heard the word borrow, I have no idea what that means, but I heard the word unexplode, that sounds way more exciting. Shall we unexplode? Very important question. What's the sound effect we're going to have for unexplosions? I heard it. I have to do a sucking sound. Okay, here goes. We're going to unexplode. I assume you mean unexplode one of these. 1 less there, 10 dots here, and that makes an extra 10 dots there. But there's some annihilations. Poof, poof. So I guess that's really 8 dots there. 280 negative 2. Absolutely solid, absolutely fine. No worries with that question, that answer. Though, society is demanding. Unexplode again. So 1 less dot there, extra 10 here. So there's extra 10 there. Poof, poof. 278. Is that right? Beautiful, beautiful. Okay, I know my answer of going left to right is kind of weird, but part of me says maybe we should really encourage this because look, what's that 3 really? It's really 300. That negative 2 there is really negative 20, and that 2 there is negative 2 there is really negative 2. Do you see the answer 278 just sitting there? Yeah, I'm kind of serious. I kind of like left to right. Yeah. All right. Bingo. So addition, subtraction, multiplication. That leaves long division. Now we're to the very true part of today's story. Very true. Back in Australia, grade 5, I was about age 10, Ms. Delaney's class. We were being taught long division. I remember being absolutely cognizant of being taught an algorithm that was totally bizarre and alien. I was in a system that didn't let me ask questions. I did not understand what I was doing. I was absolutely cognizant I did not understand what I was doing, and I was performing for the school system. I was performing. I was dubbed a very good student. I was getting little happy faces and stars on all my worksheets, but I was absolutely aware I did not have a clue what I was doing. I was just performing. This is true. We were doing things like this, 276 divided by 12. And we were taught a truly bizarre algorithm back in Australia some, 42 years ago. Do you want to see the algorithm I was taught back then? The answer is always yes, by the way. Yes. All right, here goes. We had to draw a really strange symbol first. We had to draw this. Uh-oh. We had to write the big number under the symbol and the smaller number to the left. Okay? Now, I had been trained at this point for 5 years that I'm to read left to right in every class except math class. Math is always right to left. They trained me well on that one. 5 years of training me, math is right to left. No, we'll just go left to right this time. Let's switch directions. Bizarreness number 1. We had to look at this number 276. We had looked at the 2, and we asked, how many times does 12 go into 2? And you said, don't be silly, 12 doesn't go into 2. So we had to look at the 2, 7, 27. That's my second bizarreness. Am I allowed to call that 27? Because it's actually not 27. It's part of a number that's 276. So I found that curious as well. Anyhow, my job was to obey, so I obeyed. You say, how many times does 12 go into 27? You say, twice. You had to write the 2 on the top, and apparently alignment really mattered. This was the nerve-wracking part. It really was. That was scary, where the 2 goes. Anyhow, then in Australia, we had to actually write 2 times 12 is 24. We had to actually write that. Do you guys, so you're all nodding with it. Do you have to do this as well? Yeah. Okay, exactly. Exactly the same. Okay, bizarreness number 3 or 4, I'm not sure we're up to. You know what? Let's just do a subtraction problem. Why not? Let's just subtract. Why not? Sure. 27 take away 12, 24 is 3. Okay, that is pretty bizarre right there. But now comes the kicker of bizarreness. In Australia, we had this 3, and we said, well, there's still a 6 up there. We had to actually draw little arrows, bring the 6 down, and that 3 just magically changes to 36. It just changes. Weird. Then you go, how many times does 12 go into 36? Goes in thrice. 3 times 12 is 36. Do another subtraction problem. Why not? Get 0. Apparently that's good. Yep. Is that familiar? Okay. It's really hard for us adults who have been so well trained in that algorithm not to equate familiarity with understanding. That is so familiar that we feel like we understand it. But actually, if you really try to step back from it, it is as bizarre as heck. It's hard for us to imagine seeing it for the first time. And what do our students do? See it for the first time. Anyhow, so apparently if you do 276 divided by 12, you get 23. Is that the answer? All right. So let's have a little moment of therapy for young 10-year-old James Tanton. Now that he's 52, let's help him out with this right now. What really went on with that? Well, first of all, we got to ask what's division. I mean, there's a number of ways to think about division, but one very obvious way to do division, and this is a valid algorithm, I could do this. I could literally draw 276 dots on the page. I'm doing it again. And I'm really asking, how many groups of 12 can I see in my picture of 276? So I could literally just go ahead and just start circling groups of 12. If I really had the patience for that, how many groups of 12 should I find, allegedly? 23. Okay. So that's valid. It's just awfully tedious. But let me do that approach with something a little more sophisticated. Let me draw a more sophisticated picture of 276. Let me do it in a 10-1 machine. 270, T-Y, 6. Yes? 12. What does 12 look like in a 10-1 machine? 1 dot and 2 dots. Now, I'm going to be very careful here. In my first picture, I was literally circling pictures of 12 dots, 12 dots, 12 dots, 12 dots. I didn't actually physically draw 12 dots here. But there are 12 dots in this picture. Where are the 12 dots in this little sub-picture? They must have all been here, so they're all in that rightmost box, but then an explosion went kaboom, and left 2 behind and spilled 1 over. So actually the 12 dots really are there, they're all right there, just got hidden. Spillage happened, pushed me 1 spot over. All right, that's what 12 looks like. Do you see any 12s? Do you see any 1 dot next to 2 dots in that top picture? Anywhere? Yes, the answer is always yes. 1 there, is that right? There's 1 at, I say, where are those 12 dots actually in that loop? Are they in the left part of the loop or the right part of the loop? The right part, they're all there, 1 at that level. Any other 1 dots next to 2 dots? Yeah, loads of them. Any more? And again? My loops are getting weird. 1 more? Okay, really weird loop. So I'm seeing 2 at the 10s level, 3 at the 1s level. Now I'm pushing you guys fast. I'll go slow with younger kids, but you're kind of with me? Yep. We're seeing 23, 2 at the 10s level, 3 at the 1s level. And in fact, this is what's going on in this algorithm. This is what really was going. We were, of course, doing the correct math. When I was first asked to look at 27, which was bizarre to me, what am I really doing? I'm not actually looking at 27. What am I looking at in my picture? I'm focusing on 2 dots and 7 dots, is that right? I saw 2 groups of 12. I wrote 2 groups of 12. Oh, I wrote 2 groups of 12 over here as well. We're in sync. What's the subtraction business about that's a bit bizarre? What am I really doing with the subtraction? Yeah, I've dealt with those. I've got 3 dots still to contend with. This weird thing about 3 magically becomes 36. What am I really doing? Just focusing my attention on those 3 dots and the 6 still that's sitting there under my hand. And I've found 3 more at that level. Bingo, I'm actually in sync with that algorithm. The algorithm, of course, is fine. The algorithm's great. But I'd much rather draw a picture. In fact, should I do a really juicy one right now? Yeah. Let's do a hard one. You guys are ready for it. What is 31825 divided by 102? How's that? Is that juicy? Yes. All right, so let's just draw a picture of it. I don't mind spending an extra 5 seconds of my life drawing a picture. This is kind of fun. 3 10,000s, 1,000, 8 tens, 8 hundreds, 2 tens, and 5 ones. Yeah? Yeah, ausgezeichnet. All right, what does 102 look like? The board's getting a bit crazy here. What does 102 look like in a 10-1 machine? Yep, 1 blank 2. Yes? Now, all 102 dots really were there, but a lot of explosions and spillage must have happened. Yep. All right, so the game is now, can you see any 102s, 1 dot blank 2 dots in that picture of 31,825? Yes, good answer. For example, 1, nothing, 2. At that level, they're all in the right part of the loop. Any others? Yeah, another one at that level. 1 blank 2. Okay, my loops are getting messy. Can I just do 1 blank 2 like that? Can I do a split loop? You with me? All right. Any more? Yeah. 1 blank 2. Any more? In fact, I'll do a double hitter. 1 1 blank blank 2 2. Was that too fast? Was that okay? Any more? No. We've got 1 left over. Ooh. So how do I interpret that answer? In fact, what is the answer? 3 1 2, but we abandoned that dot. Okay, so remainder. So if you're in grade school, you write remainder. In America, do you use the letter R for remainder? Is it big R or small r in this country? Because whatever it is in this country, we're doing the opposite in Australia. I can't remember which one's for me. I think I was little r in Australia. I think Americans are big R. Remainder 1. In Korea, I think they go ... 1, if I remember correctly. Was anyone else taught anything different how to write remainders in math class? I'm curious. Well, okay, and the actual math answer is plus 1 more dot still waiting to be divided by 100. That's the actual math answer. Yeah, so I shall go with that one personally. But there it is, long division. Piece of cake, all with a picture. Great. But now you're wondering, hang on, you're a high school teacher meant to be teaching kids polynomial division. Why was I doing all this with my high school kids and college kids, every kid, parents? The thing is, math does not care about our humanness. It doesn't care one whit that we have to be born with 10 fingers, 10 digits. In fact, we could do everything in Martian and it'll be fine. We could do everything in binary And it would be fine. In fact, it is fine, because computers are what? And why? Why are computers binary, actually? Why would you say that computers only have 2 digits? Because they are electrical switches that are either on or off. They've got 2 symbols. So everything should be in 2 symbols. Binary is natural for that. All right. So what I'm going to do now to prove that I'm right, that the math doesn't care which machine we're in, I'm going to repeat this entire lecture, or most of it, in all machines all at once. I'm going to do it all in one grand hit. Are you ready for it? Because the answer is yes. All right, I need my eraser. So what I'm going to do, how I'm going to do it is I'm going to draw a machine on the board, and I'm thinking of a particular number. It could be a 10-1 machine, could be a 7-1 machine, but I'm not going to tell you what's actually in my head for the machine. It's the mood I'm in. I'm not going to tell you what I'm thinking. But here's a machine. If I get the pen open, there we go. It's some machine, that's it. I've actually got a number in my head, I'm just not telling you. Now, just to give a nod to algebra classes and teachers and textbook authors and textbooks all across the globe, there seems to be one particular letter of the alphabet everyone's obsessed with. If you don't know what a number is, you might as well just call it X. Math doesn't care, it can be any number you like, any letter you like, or any symbol you like. I used to have my kids draw a little fish or something sometimes. Anyhow, X. So just to give a nod to algebra all across the globe, I will call this an X1 machine. And I actually do have a number X in my head. Could be a 10-1 machine, X is 10, not telling you. Could be a 3-1 machine, not telling you. Okay, so the question is, what do you know about this machine? The answer is really nothing. Well, actually, no, you do know something. You do know that dots here are always worth 1, because that's how the game was set. 1 dot, 1 dot, 1 dot. And you do know that X of these, X1s, makes 1 of those. So a dot here better be worth X. And you do know that X of these, XX's, is meant to make 1 of those. So XX's must be X squared. And XX squared makes 1 of them's. X cubed, X to the 4th, and so on. So you know that much at least. Yeah? Now, just check. If I really am thinking 10 in my brain, is this correct for a 10-1 machine? Are these the right numbers? 1, 10, 100, 1,000? Yep, that's the 10-1 machine. Or if this really is binary, if there's X is 2 in my brain, 2-1 machine. Is it the correct numbers for 2? 1, 2, 4, 8. So yes, this really does represent all machines all at once. All right, so we're just over there. We're doing grade 5 arithmetic. No warning. Let's leap up to grade 11 high school algebra. I want to know right now what 2x squared plus 7x plus 6 is divided by x plus 2. High school teachers are yelling at me right now because we're in my parentheses, so I'll use a vinculum. I want this divided by that, please. And suddenly we have a scary moment. Like gulp. That looks terrible. Welcome to high school algebra. So, here's the thing about doing mathematics. The first 2 steps to problem-solving mathematics are 1, be your human self and have an emotional reaction. I'm serious. If that looks scary, say, it's scary. If it looks joyful, say, wow. Just be your human, acknowledge your emotion. Step 2, take a deep breath and do something. Anything. Go for a walk, draw a tree. Maybe do something relevant to the problem. Just do something. Can we do something right now? Can we at least draw 2x squared plus 7x plus 6? Is that drawable? Yeah, so we do that. So 2x squareds, 7x's, and 6 1s. Is that right? 2x squared, 7x, and 6 1s? Yes. What does x plus 2 look like? Dot, double dot. Is that right? 1x, 2 1s. So apparently we're looking for 1 dot next to 2 dots in this picture of 2x squared plus 7x plus 6. Do you see any 1 dot next to 2 dots anywhere? Why? Yes. There's one there at that level. Another one? Any more? Yeah? My loops are getting a bit weird. Well, this one's getting really weird. So how do I read that answer? It's 2 at the x level, 3 at the 1's level. The answer must be 2x plus 3. Now, the real question is, did that feel like déjà vu? Do you feel like you've done this before? Do you feel like you've been here today? I think it's an identical picture, isn't it? High school polynomial division is just a repeat of grade 5. It's just in base x rather than base 10, and no one tells you. There it is. In fact, if I told you I really was thinking x was 10, this really was a 10-1 machine in my head all along, What is this? What's 2 times 10 squared? 200 plus 76 divided by 10 plus 2 is 12. Apparently equals, of course it is, we did it over there. Whoa. High school algebra is just a repeat of grade 5. Thank you, grade 5 teachers. You've done my job as a high school teacher. And I'm actually kind of serious. We're all in this together. It's a beautiful story for our kids. And look how we can help each other out from K all the way up. It is amazing. Pity everything I just said to you was a lie. It doesn't work. I did a carefully constructed example that works out nicely in this carefully constructed situation. Do you want to see what can go terribly wrong with this approach? Unfortunately, the answer is yes. Yes. Here's what can go terribly, terribly miserably wrong that proves I'm a liar. After all this excitement, I don't know what these 4.8 million kids are excited about because I'm a liar. Here it is. Here's what can go woo, horribly, horribly, horribly wrong. Let's try this one on a smudgy board. X cubed minus 3x's plus 2 divided by x plus 2. I'll do x plus 2 again, since it's our friend. Can you see what I carefully avoided? Yeah, that negative number, those Todds. So let's see. Can I at least draw it? Can I draw the numerator? Can I draw that top thing? Yeah, I can draw that at least. So it'd be 1x cubed, no x squareds, 3 Todds is it? Todd, Todd, Todd. And 2? Yep. Just remind me, what does x plus 2 look like? We've done it 1,000 times. But 1 dot next to 2 dots, is that right? This one is so bad. Do you even see 1 dot next to 2 dots? No. Well, thanks for coming. This has been great. So there we go. Oh, fix it. Well, that's an attitude. All right, okay. So let's fix it. I will follow your lead. So, any ideas on how to fix it? Suck it up. Oh, you mean unexplode? Unexplode. Brilliant. Actually, that worked on 2 levels. Suck it up. Toughen up, Tanton. Do it. Fix it. And then let's unexplode by sucking it up. Okay, so assume you see this dot way over yonder. It seems very natural to unexplode. Is that right? Then let's do it. How many dots do I draw here? Oh, it's an x1 machine. You don't know what the number x is in my head. If I told you it was a 10-1 machine, you'd draw 10 dots. It'd be fabulous. If I told you it was a 3-1 machine, you'd draw 3 dots. It'd be fabulous. Now, we could try to abstractly draw x dots, but that feels hard to me. But maybe it work. Maybe you can make it work. That'd be great. So welcome to mathematics. That was actually a brilliant idea. That was a genuinely brilliant idea, and I mean that. But often happens in math. You have a brilliant idea, and it just turns out not to be helpful. Welcome to math research. Yep, that's how it is. Okay, well, that was great. That was fun. Thanks for coming. Yeah.
Add a dot to the top.
All right. This young lad here just hit upon why I absolutely loved being a high school teacher. It's actually this very moment. This very moment. Because he just hit upon what I'm really doing here. I'm teaching a life lesson. And I mean it, literally a life lesson. Because right now is a life lesson. This lesson is, if there's something in life you want, make it happen. And deal with the consequences. Because you can't help but notice there's this dot here. What would be so nice to have there with that dot? What would be like the ideal thing to have in life right now? Two dots, because you're looking for 1 dot next to 2 dots. So here's my piece of advice. If there's something in life you want, make it happen. Here it goes. There, I made it happen. Now deal with the consequences. Because this box is meant to be empty. I can't just willy-nilly put dots in places. So how do I keep this box technically empty? Add 2 Todds. Is that box still technically empty? Okay. This feels good because I can at least see that. Yes? Okay. The question though, was it helpful? It was actually brilliant. That was a brilliant move. But was it a helpful move? Yeah? Oh, I heard 2 things there. Okay. Let me focus on this for a moment. Do you see these 2 dots here? Anything you'd like to have to go with them in life right now? You would love to have a dot there. So I have a piece of advice for you. Make it happen. Deal with the consequences. Yep. So far so good? Voila. Still feeling good. Feeling very good. But is it helpful? Yeah? I'm hearing it. You look at this, one Todd next to two Todds. Is that the complete opposite of what we're looking for? Is that an anti-version of what we're looking for? We found one anti-version and another anti-version. Whoa, it worked out. How do I read that answer? X squared, take away 2x, negative 2x plus 1. Beautiful. I was lying about lying. It actually works out just fine every single time. Do you want to do a really hard one now? Yes, we'll do a really hard one right now. Let's try this beast. Let's try. Oh no, what am I doing? I have to write the problem. I would like x to the 8th minus 1 divided by x minus 1. Yes? Now I'll draw my boxes. How many boxes do I need to draw? That's probably the hardest part. 8 boxes? Yes, because the x to the 0, x to the 1, x to the 2, up to the x to the 8. 9 boxes. We have one x to the 8, and we have one anti-1. Pretty sparse picture. What am I looking for in my picture? Dot, anti-dot? Yes. Oh, I don't see any. I shall weep. A little weeping moment. I know you're thinking it. What do you want me to do? Is something in life you want? Make it happen. What do you want to go with this one? You want a Todd? Make it happen. Deal with the consequences. Bingo. Again? Make it happen. That's great advice. Am I just going to be, oh, this is too ridiculously nice. How am I doing? Oh, and look, and the final one works out. So how do I read that final answer? 1 plus x squared plus x cubed plus x fourth plus x fifth plus x sixth plus x seventh plus x squared. I think I skipped it. Do you want to do another one? Let's take this up a notch. This is high school algebra. So my kids could do this just fine. We were done. We were done with polynomial division. There it is. And it became a joyful experience. But then there are other things in the curriculum and beyond that also need attention. For example, I was meant to teach kids a very famous formula which looked like this. Take the polynomial 1. It is so simple that it makes it hard. What I mean by that is just one dot. You know, you have like, it doesn't matter how big your machine is, the polynomial 1 is just one dot in the ones place. That's it. Pretty sparse picture. Nonetheless, please divide this by 1 minus x. All right, first of all, 1 minus x. What does that one look like? Okay, so it'll be negative x and a 1, so it's Todd dot. Do you see any Todd dots? No, but we're not perturbed because we can take action in our lives. You want a Todd dot? Make it happen. You want Todd dot? Make it happen. Deal with the consequences. Yes? Anything else in life you want right now? I'd like a vanilla latte. There's a Starbucks over yonder, I believe. So. Do it again. Todd dot. Beautiful. Again. Beautiful. Again. Beautiful. Again. Beautiful. Again. Again. I think we're going to be here for a very long time. So the question is, it's going to be an infinite process, but how do I read that answer? Yeah, how do I read that answer? A 1 plus an x squared plus an x cubed plus an x to the 4th forever. forever. Is that right? Beautiful. Have you seen that formula before? It's called the geometric series formula. If you like it to be fancy, it's the Maclaurin series for the rational function 1 over 1 minus x. In schools, they tend to write this part first on the left, and they put this part on the right, as in the answer to the infinite sum is 1 over 1 minus x. They tend in school books to call it not x, but r's. And just to make it look really scary, multiply everything by a. Am I serious? Is that the formula you see from textbooks? Yeah, let's make it as really cluttered and complicated as possible, please, for those poor kiddos. Grand. Bingo. Infinite series from calculus right now. So, the story doesn't end there. I've got two directions. This is now like audience choice. Do you want me to stay in the K through 12 world, or do you want me to go to unsolved research territory? One is a little more dangerous than the other. Which way shall I go right now for the remaining 5 minutes? You bet the unsolved. Of course, who could resist that? This story is phenomenal. It just unfolds and unfolds. All I'm doing is kindergarten math, playing with dots and boxes. Actually, all I'm really doing is nothing new to the world. I'm playing with an abacus, which has beads on rods instead of dots and boxes. That's a very beautiful visual way to have a visceral, and I mean visceral, understanding of place value and understanding. If you see that, you own it. So let me get quirky. Let's have fun. I'm a mathematician, like to play. So I did a 10-1 machine, talked about 2-1 machines, 3-1 machines, and so on. Let's get strange with our numbers. First of all, a 1-1 machine. My only question is it interesting? I mean, that's a subjective term. Maybe yes to you, maybe you love it, maybe you don't. Can you do anything with it? What happens if I put in a dot? Kaboom! Kabow! Because it just shoots off to infinity. It's kind of untamable. We can't do much with it. All right. What about a 1-2 machine? Put in one dot, what happens? Kaboom! But it becomes 2 dots. Kaboom! Kabow! Dot, 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 dot. So it's going to just keep going off to infinity, but it's expanding out like all this expanding shrapnel going off to infinity. Okay, pretty untamable. What about mix up the numbers? A 3-2 machine. Whoa, that's juicy. Okay, let's play with it for a moment. Put in one dot. Zoom. What do you get? One dot. Put in a second dot. Zoom. Still saying 2 dots? Put in a third dot. Zoom. 3 explode, kaboom, and become 2. So what's the code for 3 in a 3-2 machine? 2, 0. Put in a fourth dot. Zoom. 2, 1, is that right? Put in a fifth dot. Zoom. 2, 2, is that right? I have a feeling putting in a sixth dot is going to be particularly exciting. Am I right? What are you going to get? Put in a sixth dot, what will you get? Can you see it? Here, I'll do it then. Zoom. Kapow! Dot, dot. Kaboom! Dot, dot. So what's the code for 6? 2, 1, 0. 13. Let's get some numbers again. Not as swift this time, are we? This one's tricky. 2, 1, 2, 1. 2, 1, 2, 1. Okay. I don't know. I don't know if it's 2, 1, 2, 1. But, so Po here is doing arithmetic. Because in ordinary arithmetic, he said he doubled the 6, 6 plus 6, and then added one more. In ordinary arithmetic, what is 6 plus 6 plus 1? 13, yep. Now, in whatever this is, what's the code for 6? 2, 1, 0, plus another 2, 1, 0, plus one more. If I did this, and I'll go left to right, 2 plus 2 is 4, 1 plus 1 is 2, 0 plus 0 is 1. But what's going to happen with that 4? Yep, so 3 would explode, leaving what, 1 behind? Kaboom! And 2 dots there. If you can do arithmetic in this machine, then the answer seems to be 2, 1, 2, 1. In fact, let me check. I'm really slow. I'm a very slow thinker. I'm going to actually put in 13 dots and check what we get. Because this is my brain. I'm slow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. 3 explode, become 2. Here goes. Kaboom! Dot, dot. Kapow! Dot, dot. Kazing! Dot, dot. Kazlooble! Dot, dot. Did I do that correctly? So easy to make mistakes. More explosions? Kaflooble! Dot, dot. Kaflingle! Dot, dot. Yep. Kabibblebop! Dot, dot. 2, 1, 2, 1 is actually correct. But the real question is, what is this machine actually doing? Are we in a base still, or are we doing something totally weird? Base 1.5, kind of. Shall we try to figure it out in the remaining 2 minutes? Yes. Yes, good answer. Let's see if we can do it. Let's see if we can do it. Okay, dots here are always worth 1, that's for sure. But 3 of these is equivalent to 2 of those. So 3 ones is 3, but 2 of those makes 3. So what must each dot here be worth? 1.5, 3 halves. Can I write 3 halves? Okay, I don't know what the curriculum allows nowadays. Okay, great. 3 3/2 is the same as 2 of these. Now it's getting harder. Okay, here's how my brain works. I don't know what this is. I'll just write W for I don't know what. I'll choose letters that make sense. But I know that 2 watts, whatever they are the same as 3 3/2. Yep. Does that help? In fact, divide both sides by 2. W is 3/2 times 3/2. 3/2 squared, which is 9/4. Looking good. Let's do one more just to check. 3 of these is the same as 2 of those. So, I know, what letter do you want for this one? Your turn. Silence. Okay, silence. S. So 2 silences is 3 3/2 squareds. Great. So what's silence? 3/2 cubed. Welcome to base 1.5. 1.5. Sorry, I should say with the right inflection. Welcome to base 1.5. We've just discovered fractional bases. And this, I will tell you, freaks me out. This feels intuitively wrong. Look at these fractions. 1 3/2, 9/4, 27/8, 81/16, 243 32ths. Crazy fractions. Yet apparently, if you take this combination of those weird, horrible fractions, it works out to be 13, a good solid whole 13 on the nose. That actually seems unbelievable if you pause on this. Yeah, so I'm going to check it, because I actually personally don't believe it. My gut says to me that cannot be so. So apparently, 2 27/8 plus 1 9/4 plus 2 3/2 plus 1 1. Does that work out to be a big whole number? Yeah. 27/4 plus 9/4 makes 36/4, also known as 9, plus 3 plus 1, it's 13. Who would believe that the combination of those really weird fractions turn to be whole numbers each and every time in this machine? It's actually unbelievable. Welcome to base 1.5. Here's optional homework tonight. Go back to your textbook, whether you're studying from a textbook or writing a textbook or teaching from a textbook, and rewrite everything in base 1.5 for your students. It'll be fine. Did you hear the word optional? Yeah. You know what optional means. It means don't do it under any circumstances. Yep. This is amazing. This is absolutely amazing. And mathematicians have so many unanswered questions about base 1.5. All it is the powers of 1.5 are still deeply mysterious in the math community. Powers of one of the simplest fractions around, it still has unknown issues to it. For example, I kind of like the number 17 in this base, because 17 turns out to be 21012. It's a palindrome in base 1.5. Though I have to be careful with my language base 1.5. Most mathematicians think I'm weird talking about base 1.5 right now because they always say the coefficients should be smaller than the base number. So I'm doing a version of base 1.5 that uses the digits 0, 1, and 2. So I'll just be clear, it's like not the usual base 1.5. But it's a palindrome. There are only 10 known examples of palindromes in this 3-2 machine. 17 is one of them. Only 10 are known. You might notice that all the numbers begin with a 2 after the first hiccup. Does it make sense all the codes should begin with a 2? Can you see that in your mind's eye why that would be true? Yeah, because in order to get to the next digit over, the only way it comes from an explosion, and it's 3 become 2. So there'll always be a 2 at the beginning. But if you play with this for a while, you notice they all start to begin with 2, 1 after a while. Does that make sense? And then you might want to keep going. See, do they all begin with like 2, 1, I don't know, 0 or 2, 1, 2 after a while? What are the distribution of those 2, 1s and 0s? Do they all appear equally often in these codes, or does one number get predilection over another? The big question no one really understands at all is like, when do we jump up to the count of digits? For example, when we got to 3, that's our first 2-digit answer. 6 is our first 3-digit answer. 9 is our first 4-digit answer, it turns out. 15 turns out to be our first 5-digit answer. 24 turns out to be our next 6-digit answer. Any predictions about what the first 7-digit number is? 3, 6, 9, 15, 24, 39. Excellent, because it turns out to be 36. It looks like it's going to be Fibonacci-esque for a while, and it just breaks down. No one can find structure in those numbers. You can find patterns that last for a while, and then, gone. Go away. And all it really is just trying to understand the powers of 1.5. So all we've done today is taken beautiful, stunning, gorgeous kindergarten math, dots in boxes. In fact, there was a beautiful tweet that went out 2 days ago of someone who said, this teacher must have been doing something in their school class because she went out to the schoolyard, the kids had taken sidewalk chalk, drew some boxes on the asphalt, and were using stones, and one kid was explaining how to do arithmetic in Martian to another kid. Because he decided Martians had 6 fingers, and was doing everything like 6 explode to become 1. How do you read the number 12 in Martian? Just put the stones in the boxes and did it all out. That's what 12 is in Martian. Beautiful. A portal to joy and wonder and play and human connection, a human story. Let's set Math 3 to let it shine for itself. So thank you for being part of Global Math Week. Let's make it happen. Really appreciate it.